Welcome back, guys. It's the morning today. We're gonna do a few problems. I don't even know. I think 78 Pokemon. Wait, 76? Yeah, I think it's 76 today. Yeah, we did Gravelly yesterday, so 76 today. We got Golem. We got Golem today. We're gonna check out the sound. Golem sound. Okay, we're getting a Minecraft Golem. You want a Pokemon? Take a look here.
The hot, crispy filet o fish with soft steamed buns, tender, flaky fish, melty cheese.
Dun, dun, dun. That's our sound right there. Dun, dun. Turn on my headset a bit. Dun, dun. Okay, that's cool. Nice. Alright, we're gonna take a look at a few problems today. We're just going through our Leetcode 75 and our powerful study program. We'll check out our problem of the day first, though. I thought problem of the day was Tucson, bro. No way. This was the same one yesterday that we checked last night, so we're gonna leave that. 30 days of JavaScript. Alright. What we'll do is we'll take a look at our powerful study program, which is here. I think we finished all of these, right? I think nearly. Which ones are we missing? Subarrays, is equal to k, h index for some. There. Binary trees. We're nearly done with this one. Path sum, easy. Path sum 2. Let's check out check out this one. I think we did this one yesterday. I wonder if this is the same thing. Lowest common ancestor of a binary tree, of a binary search tree. Is it the same question, then? Given a binary tree, find the lowest common ancestor of two given nodes in the tree. According to the definition, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T, such that P and Q as descendants where we allow a node to be descendant of itself. We return itself. Okay. Man, I'm definitely cold. I don't know what is wrong with my microphone right now. P is equal 5, Q is equal 1. The intuition doesn't come to me here. No, we literally did this problem yesterday. Like, at least I think it's like pretty much the same problem. I don't really remember how I did it. The root is equal to P. Sorry. Return root else if to think recursion stuff from the root and traverse down. If you find either P or Q, return it up the recursion stack. Root dot left is greater than P, and root dot right P dot val is greater than root dot val, and Q dot val is less than root dot val. What does that mean? P dot val is greater than root dot val. Okay, this won't work because this is a binary tree, not a binary search tree. So think we do have to think recursion here. You've either P or Q, return it up. P, Q. If P, no. I don't know. It's tough. I'm gonna give a binary tree with 2 nodes, P and Q. The goal is to find the lowest node in the tree that both P and Q as descendants. Or root is equal to null. Node dot left for DFS node PQ. Node dot left PQ. Node dot right is equal to DFS node dot right PQ. And then they have some sort of like ternary operator here. If left does not equal null and right does not equal null, we return the root. If left does not equal null and right does not equal null, no, we return the root. Otherwise, we just return if left and right, return the root. Otherwise we return left, else right. If not root or root is equal to P or root is equal to Q, we return the node. Oh, there's no attribute left. Node dot left, node dot right. Just realized node. It's just so hard to think about this, like, for me, like, recursively, like, the way you think about this, right? Like, you start at 3, right? We loop through, we go, well, if not node, or node is equal to P, or node is equal to Q, right? In this case, it doesn't, right? So then we go, we call left. We go left, right? We loop through, well, node is equal to P, so it returns a node, so we return here, come back to 1, then we call right. We go right, it returns that one back to there, so it goes back to 3. Now we're at here and we do, well, if left and right, we return the root, right? So we return 3. Otherwise we return left, if left, else right. It's like, bro, I can understand how it works, you know?
Glorious about trying to do easy things. There's nothing glorious about not stretching yourself outside of your comfort zone. And I think one of the root causes of the depression and the anxiety and the self-loathing.
Sorry, that was probably loud. Anyway. It's tough to think about that recursively, you know? Anyway, we're going to jump to another problem. I think we should be able to get that next time. I think I should be able to get the base case. Failed to pass your input. Please check again. What the... Did they update this website, bro? Let's take a look at path sum. Give it a root of binary tree and integer target sum. Return true if the tree has a root to leaf path such that adding up all of a's on the path equals target sum. A leaf is a node with no children. Here we go. Five, 9, 21, 23. Wait. 5, 9, 20, 22. Oh, okay, target sum is 22. Damn true. Okay. This is obviously DFS right here, right? I think we can do this recursively all iteratively, so we'll do both. Alright, so I think we'll start iteratively. We'll define our stack. We'll put in our root. We need two values, root and our cosum, right? All stack. I gotta set my streaks real quick. Okay. We'll do wall stack. Then we want to do, well, we want to pop our node and our cursum, right? Cursum is currently 0, so okay, cursum is equal to stack.pop, right? We want to go through and we want to do, well, cursum plus or equal to node.val. We add the cursum. Okay. We do, well, if node.left, then we do stack.append node.left cursum. Need the double parentheses so we can iterate through this. So we want to do a if node.right node.right cursum. Want to return cursum. I should no, sorry. Cursum, we need to do a max, right? Oh, wait. We add cursum. We have to check, well, if cursum is equal to target sum. Then we just want to, we can return true in this case. Otherwise we go through here and we just return false. If it never gets it. Non-type attribute error has no attribute val. Why not? Can't access local variable node. Okay, if not root, sorry. That's what I meant. Okay. Ooh, we're missing it. Okay, what do we got here? Expected false, but we return true. Oh, it's because we're not checking if it's a leaf node. Okay. If curse sums equal to target sum. And root dot left is equal. Curse sum is equal to target sum and not root dot left. It's equal to none and root dot right is equal to none. Okay, that does not work. I think the reason why this is not working is because we're not checking if it's a leaf sum. I think the reason is because it's not checking leaf node. How can the only way I could think about checking the leaf node is doing it within this curse statement here. Bro, that's literally what I did, bro. What the hell? I literally did this. And not no dot left and not no dot right. Isn't that what I did, bro? Am I tripping or did I not do this? Like, bro, what did I do? Oh, I'm checking root. That's why. Oh my god. Bro, stupid mistakes. Oh, it should be not. Nice. Okay. Cool. Let's do a let's do a recursive function, right? So we do while def DFS. We want to pass in our root and probably our curse sum, right? I would assume. I think. I guess if not root. Curse sum is equal to target sum, and we want this to be node, and not no dot left, and not no dot right. We want to return true, right? Not node, return. Then we want to do, well, DFS, root, and 0. We'll return false if it goes through here, it doesn't get anything. Do well, custom, sorry. Root dot left, sorry, no dot left. This is equal to DFS, no dot left. Dot left custom, no dot right. Equal to DFS, no dot left, no dot right. Custom. Probably want to add it up here, right? We do custom plus or equal to no dot val. That worked, dude. Maybe I'm not sure. Like, DFS is not returning a boolean properly. Okay, if not no, we return false. Return false instead of none. Okay, sum false equal to no dot val. Return true. Okay. Get rid of this. We want to return. With custom. Oh, DFS no dot right. Custom. Okay. Okay. Interesting way to do it. Alright. jump into our Leetcode 75. Ooh, we're positive now if I want. Solve 16 problems. Let's go, dude. Let's take a look at our decode string. Might as well do this one. Kind of want to jump back into do some greedy problems. How to use sorting, how to understand the logic of some basic problems, and make things some master degree items just to practice a lot. Okay. Alright. Given an encoded string, return as decoded string. When did we do this? November 6th, 26. Okay. Amazing. Okay, the encoding rule is k encoded string, where encoded string inside the square brackets is being repeated exactly k times. Note that k is guaranteed to be a positive integer. Okay. Okay. There are no extra white spaces, square brackets are well formed, etc. Furthermore, you must assume that the original intent. I kind of have to think how we're going to solve this problem. We have solved it before, so let me think. Let's maybe jump up a paint here. What's the best way to solve this? With a stack. Maybe we loop through this. Okay. So we have a 4, right? We loop through this string. For each 4, we check, well, what it is, right? If it's a number, right? I guess we can add the number to the stack. Right. We can add it to the stack, ignoring we use a stack to store the number, right? Then we get to the actual letter, right? We add the letter here. And then as soon as we see the empty square, right? Then we add everything here, right? So we pop from the top. We have A. We have A times 3. A, right? Then we go back and we see a 2. We add 2 to the stack. Right? And we see a B and a C, right? We have our string BC. That's kind of what I'm thinking, but I don't know if that's maybe the way to go about it. I have no idea. Like, I don't know. Trying to think.
That's kind of what I'm thinking here, and I think that's what we're going to start with. So we'll do for I in, okay, for value in range length string, right? And we check, well, we need to create a stack, right? We have stack is equal to this, right? If s value is equal to, I think, a square bracket, we can just continue, right? Else if s value is equal to also if s value dot is digit, then we want to add it to the stack. So let's append it to our stack, right? Stack dot append s value, right? Else if our stack check if there is alphabet is alpha, okay, dot is alpha, then is alpha. Is alpha we want to add, right? So shit. Curve plus or equal to curve plus or equal to s value, right? Else if s value is equal to a closing bracket, then we want to do stack dot append cur. We want to make cur equal to the empty string for that next value, right? Now let's print out stack. Okay, we got them. Now we want to rebuild our string, right? So this while stack -1 while stack right? We want to do, well, what are we returning here? Returning a string. Let's create our result list here. While stack. Value is equal to stack.pop. Is alpha. Alpha we want to make. Res plus or equal to I'm curious. that was close. We have our cur string. Okay, we need a cur string, cur num. Is digit. Those multi-digit numbers, what? Is equal to cur num times 10 plus char. Why do we do that? That's interesting, dude. You thought about it the right way, you know, but I don't get this here, right? I don't understand why we times it by 10, okay? I don't understand why we append something that's empty. Ah, okay, there can be more. They can be like, okay, like nested ones. Okay. Test case. On 3, okay. Okay, yeah. We see stacked over current num, so we run empty string in 3. We reset it. Okay, then we add a to our current string. Then we see the closing bracket. We go to the closing bracket, prev string num. So we pop the previous 3 and empty. Make cur string is equal to previous string empty string plus num, which is 3 times the current string. We have 3 A's, right? Okay. Okay, so we're building here, that's why. This is a really interesting way to do the problem. I mean, I'm understanding this right now when you see a digit, when you see a string. But here, like, it's an interesting way to think about it because, you know, when we see the open bracket, we're appending, right, what we currently have, resetting, and then when we see the end, right, we're popping the previous and adding, pretty much adding our previous string to the num and the current string. So I would have never thought about doing. Like, it's a tough way to, like, think like that, you know what I mean? Like, trying to... Let's run through a practice problem here. I'm going to run through this one here. I'm going to run through it with our code. All right, so we have 3 A 2 C, close this, close this. Right, so 2 CC. Okay. What we want to do is we want to come here. We see his digit, right? We return 3, right? This is our 3. Alright, so we're here. We see this, okay? We save, right? We stacked out append what we currently have, right? This is our stack. We append 3 and an empty string. Okay. 3 empty string. And then we make everything equal to 0, right? Oh shit, 3. And we're at 0, empty string, right? Okay. We see A. We append that now, right? So we append that to our current string. We have A. We see a digit, and we append that to our current num. Okay. We see the open bracket, right? So when we see the open bracket, we stack out append our current string and our current num. So we append our current string, which is A. Sorry. Current. A current string, which is A. I'm not even going to put the speech marks there, bro. I'm just going to put A and 2. Empty string. And 3. Okay. So now we're at C, right? So our current string, we append, we're at 0 now again. So we have C, right? And then we have our first closing bracket, right? So we get a closing bracket. We pop, right? Okay. We have our previous string is equal to pop, right? And we have current string is equal to previous string. So we have A plus num. And num is 2 times C, right? So we have ACC, I think. Yeah, ACC. And then we have another one, right? So then we pop again, right? So we pop the empty string. Okay, so we pop empty string. Our current string is equal to previous string, right? Which is this plus num 3 times our current string ACC. So really we have ACC, ACC, ACC. Yeah, which is what we get here. ACC, ACC, ACC. Okay. Interesting way to solve this problem. It's hard to think like that, you know. But we'll get there. Like, I did kind of think about. I did think about the is digit. I was thinking about each of these things as I was looping through, which is a good start. But, you know, just wasn't really thinking really about the stack. I think this is really tough to think about these two. Like, the way that you have to think about that is, like, extremely tough, you know. I think, obviously, probably more preparation needs to come in there. So you're just writing code. Like, you really prepare and really think about how you're going to add these things. Think about all the different test cases they provide. Maybe it'd be better, but I don't know. It's tough. That's right. We'll check out our next problem. Number of recent calls. I think I remember this one. Okay. Yeah. I do. We did this one in February. Interesting, about a month ago. You have a recent counter class which counts the number of recent requests within a certain time frame. Implement the recent counter class. Recent count initialize the counter with 0 requests. Adds a new request at time t, where t represents some time in milliseconds, and returns the number of requests that has happened in the past 3,000 milliseconds. T minus 3,000 t's. Okay. I guess we want to create self dot. From collections, import dq. Self dot enq is equal to dq okay, I think that's what we have to do. Self dot q is equal to dq. Adds a new request, so q dot append adds a new request at time t. Q dot append t like minus 3,000. I don't know, like I feel like this is a terrible Q problem. I feel like there's so many better ones. Like, okay, maybe we want to append t, right? As you cross time t, where t represents time returns the number of requests that has happened in the past 3,000 milliseconds. Do we need some sort of like for wow, self dot q0 t minus 3,000 and self dot q dot pop left. I want to return the length of q. Okay, sweet. I think that's a terrible queue problem. Honestly, it's a little pretty bad of an explanation, I feel like. Please word it decently. Okay. Take a look at one more problem. We might leave this one until tomorrow, but I guess we'll see. We want to get the last queue out of the way, because then technically we're finishing off these ones and then we're at grass. So Dota 2 Senate. In the world of Dota 2, there are two parties, the Radiant and the Dire. The Dota 2 Senate consists of senators coming from two parties. Now the Senate will decide on a change in the Dota 2 game. The voting for this change is a round-based procedure. In each round, each senator can exercise one of the two rights. Ban one senator's right. I'm a little confused. Collections, import, DQ. Q is equal to DQ. We loop through the Senate. How can we ban the other one from talking? To be honest, I'm not really too sure kind of how to approach this problem. This is interesting. Okay, so we have to create two separate queues. Okay, so let's make QD and QR is equal to DQ. For I in the Senate, if I is equal, we add everything. If I is equal to R, we do, hang on, for I, jeez, man. We need the index of Senate I is equal to R, then we do Q dot append Senate R Senate I if Senate I is equal to D Q dot append Senate I, and then we want the I here. Okay. We did our Q. Okay. Well, QD and QR. We want to do Q dot pop left. So D is equal to Q dot pop left. R is equal to Q dot pop left. We want to check, well, if R is if D is greater than R, we want to append R here. We want to do Q R dot append R plus length S. Okay, else we do Q D dot append D plus the length of S. Return radiant if Q R else, what is the other one? Dia.
No, Senate. Okay. So I would have never thought about this, but I kind of looked at, gave me a little bit of a step-by-step approach. We check the first senator in both the queues. The senator with the smaller index gets to ban a senator from the opposing faction, right? And that's here. So we're looking at R as the smaller one. So we do, so sorry, if D is greater than R, then QR dot append gets the ban faction update the queue. The banning senator goes back to the queue with an incremented position since they get another chance to act after banning. I guess we can kind of simulate this with we can print the QD, print the QR. And 1, 2, right? So we D has 2. This one has 0. D, so 2 is greater than R. So R dot append the length of Senate. So we append 2 in this case because the length is 2. Oh no, shouldn't it be 3? Wait, what? If D is greater than R, D is greater than R.
3, and then we do DQ. I think I understand. It's kind of a weird problem again, I feel like, but I don't know. Yeah, it's a weird question, man. I feel like, I don't know, I just feel like there could be so much better questions with the Q, you know? Like, I don't know. Should be pop left. That's why. The fuck? Is it all the print statements do that it doesn't like, I think? Oh, yeah. Stupid question. I think that was a stupid question, but it's alright. Alright, I appreciate you guys watching. I will see you tomorrow. Thank you.